Electric potential energy. Start with two positive charges initially at rest. This also will work with two negative charges, but we had to choose one of them. In order to move charge Q this way, a force opposite to the Coulomb repulsive force needs to be applied, right? Because if you just put two positive charges next to each other, they'll repel. We will now apply the concepts of work and energy that were introduced in the mechanics unit of this course to electric charges. Please recall that work is defined as Ft, where d is the distance over which the force is applied. If the force is parallel to the distance an object is moving, then the work is positive. If it is parallel and opposite to the motion, then it's negative work. If the force is perpendicular to the motion, then zero work is done. An external force which does an amount of work would increase the potential energy of a system by an amount delta U equals W equals work. Right? That's the good old work energy equation. Right? If you have an initial energy here plus work, that gives you a final energy. Or work is equal to delta energy. And here we're just going to be talking about potential energy. And yes, we will have a mathematical expression for electric potential energy. And please recall again, we started with force, then we went to electric field. Now we're going to define electric potential energy, which sadly has the same abbreviation as elastic potential energy, so we're just going to call it U. That's what's used in more advanced textbooks. We will find it by multiplying the Coulomb force by the distance over which the charge is moved. This math is a simplification of the calculus that is really needed, but it's a handy way to see the relationship of the change in electric potential energy due to the work done by the Coulomb force. So we have change in potential energy, Fd, here's the Coulomb force, times the distance you move, parallel, and look what happens. The r's cancel, and we have this expression here. Change in potential energy is K times one charge times the other charge divided by the distance between them. The distance, not the distance squared like we had for electric field and force. Now that's the repulsive force that's keeping them apart, but somebody is applying an opposite and equal force to that to keep it moving at zero acceleration, but still getting closer, still getting them closer together. So the force that pushes the two charges together gives us an electric potential energy, which is a scalar. Always good to work with scalars. It tells you how much energy is stored by the work being done on the charges, and is now available to return that energy in a different form, such as what? Kinetic energy. Right? If you push the charges close together, two positive charges, and let them go, they're going to fly away. Kinetic energy. Very similar to how we got gravitational potential energy. So let's summarize again here. If two like charges are placed near each other, they are a system and they have electric potential energy. Once you release them, they'll accelerate away from each other. Again, just like GPE, you lift the block up in the air and let it go, it's going to accelerate towards the ground. So potential energy is being turned into kinetic energy. These moving charges can now perform work on another system if they hit them. And here's where we're different from gravitational potential energy. You just have two positive masses that attract each other. Electric potential energy has two types of charges, positive and negative. These charges will move towards each other unless an external force acts opposite the motion, doing negative work. So what did we do here? I kind of slipped that in without saying. Here's positive, here's negative. They're going to try and get close to each other unless we do work on, let's say, Q minus here. We'd have to push it this way. We'd have to have a force in that direction. So the force is moving opposite the motion, so it's negative work. So they will have a negative potential energy. Two opposite charges have a negative potential energy. Putting together what we just had, we have two positive charges up here and two negative charges here. So as two positive charges or two negative charges are pushed towards each other, their electric potential energy will increase. Delta U will be positive. Final potential energy minus initial is positive. That means the final potential energy has increased. If there is no external pushing force, then the charges will fly apart. And then their electric potential energy will decrease. Delta U is negative in that case. what if we have two unlike charges? Well, if we move them apart by an external force, their electric potential energy will increase. Okay, it's just like moving a rock off the ground. The potential energy increases, which means delta U is positive. And if you let the rock go, what's going to happen? Or this charge, it'll get attracted again. If there is no external holding force, like we just said, then the charges will move towards each other and their electric potential energy will decrease. Delta U is negative.